Dear participants, we start our discussion of the project, Distance Graphs and Turan's Theorem. Our speaker, Lisa. Hello.
Yeah. Good morning, dear participants. We'll discuss several problems from the project and just the whole project. The problems were really hard. There were some open problems, although none of your results were obtained. I think we had two different problems on which we were thinking. First is distance graph. Oh, yeah. Distance graph with for n vertices and with independence number not greater than n. And we had several estimations on the amount of edges in this graph. The amount of edges, there were like several problems. And first we proved that it's at least 7n. In the second we proved that it's at least 8n, and there was an extremely hard problem which has an original paper behind it, that the number of edges is at least like this. However, we don't know exactly whether it is the upper bound of the minimal number of edges or it is not. And it wasn't proved during the conference, so the question stays open. And the other thing we were discussing, these are Johnson's graphs with 3 parameters, which we can think about these graphs as about a set of n elements. And the vertices of this graph, these are the subsets of this set containing R elements. And there is an edge between the vertices if the subsets have S elements in common, exactly S elements in common. So they could be drawn like this. We have S elements in common and R minus S elements here in this subset, R minus S elements here in another subset. And about these graphs, we thought about its subgraphs with Wn vertices, and we had different estimations on Wn, and according to these estimations, we had different estimations of how many edges might this graph contain, at least how many. The Turan's theorem implies the estimation that in this graph with n up to infinity, the number of edges, we can write number of edges like this in a subgraph with Wn vertices, is at least some function which is asymptotically functions f, and this function f is asymptotically Wn squared and divided by 2n. That's what we get exactly from the Turan's theorem, and I'll show now that if Wn is asymptotically less than n squared, then that's the best result we can have. How to do this? For a graph, that's all for a graph, Johnson graph, G of n, 3, 1. That means that we have subsets of 3 elements and the edge connects to vertices if their subsets have exactly one element in common. So for this graph, let me draw an example where the number of edges is exactly what we need. Yeah, that will be the problem 25. Okay, let's find Wn divided by n pairs of elements, and none of this pair will have any elements in the intersection. So these are just some separate pairs. Okay, and n minus 2 multiplied by Wn by n elements remain. They are not in pairs now. And now let's think of a subgraph that contains all the vertices that form in such a way that two of the elements are of one of these pairs, and the third element is one of these elements. So we have the number of vertices is this, and according to the estimation we have, it's asymptotically what we need. It's asymptotically Wn. And now let's count the number of edges here. The number of edges, which two vertices might be connected with an edge here? Only those two that have one of these elements in common and different pairs here. So asymptotically, we have the number of edges is the number of those elements. Multiplied by the number of the squared number of pairs we have here and divided by 2. Because each edge has 2 elements from one pair and 2 elements from another pair. That's clear. Wait. Oh, yeah, we have Wn divided by n squared. So it's like this, and it asymptotically equals this number. And that's exactly what the Turan's theorem implies. It is exactly this estimation for Johnson's graph and 3-1. That's the problem number 25. And now we'll see that for some graphs, we can get some better estimations. And we'll discuss the problem number 29. Here we have Wn and in the previous problem, Wn was asymptotically less than problems with writing, n squared. And now we think that n squared is asymptotically less than Wn. And in this case, we can get a far better estimation, and we'll get that the number of edges, we'll write it like this, is greater than some function. And this function symptotically equals 4.5 multiplied by. And in previous problem, with the side, we had And here we have n. So now we get 9 times better. And now we have 9 times better estimation. Let's prove it. So for each of, we'll have also the Johnson graph and 3, 1. And for each its element from the set 1, 2, n. Let's write in how many vertices this element exists. That will be numbers. For example, k1, k2, kn. The sum of all these k's, from 1 to n, is exactly like this, as each element, as each vertex contains 3 elements. Now let's count how many edges does this graph has. The edge comes from an intersection of 2 subsets that contains exactly 1 element. So there are at most k1 squared and divided by 2 plus k2 squared and divided by 2 plus kn squared and divided by 2 edges. However, we've now counted some extra edges as we didn't do nothing with the situation if there are 2 points in an intersection. However, let's count in how many cases there are such edges. We need to choose the intersection, and we can do it. Let's count how many of these intersections of these edges can be here. They all correspond to some vertex, and we can choose it in Wn ways. Now we can choose in 3 ways which 2 elements of this subset will choose to make the intersection. We can do it in 3 ways. And now we'll choose 1 more element here. We can do it in n ways. And we can also divide it by 2, but as we'll see further, it's not really important. So that's the number of extra edges we've counted. And now let's return back to this sum. We'll now use the inequality between the average squared and the arithmetic mean. And according to this inequality, the smallest the sum is smallest when if the sum of k's is fixed. This sum is smallest if they're all equal, and if they're all equal, they all equal to 3 Wn divided by n, and then the sum is this squared divided by 2 and multiplied by n, which is 9 divided by 2. These are exactly this 4.5 we had in the estimations, multiplied by Wn squared and divided by n. All we need to think now is why the number of edges we've counted and we didn't need to count do not matter. So let's move to another page, and I'll now show that Wn multiplied by n is asymptotically less than Wn squared divided by n. If we prove this, then this amount of edges we've counted doesn't mind if n grows infinitely. And how can we prove it? It's the same thing that proven that n is less than wn squared divided by n, which is the same thing as proving that n squared is asymptotically less than yeah, like this. Here we've divided wn, and here we put n from here to here. And now we have this estimation that n squared is asymptotically less than wn, which is given in the problem number 29, and that's the estimation we had. So the thing we've proved is correct, and we get a far better estimation than the Turan's theorem implies. And we can also prove that this estimation is bind, and we can also show some example why it is so, but I think we won't do it here. However, this was only proved for Johnson's graph N31, and for Johnson's graph and RS, we have an estimation in K. That will be problem 33. We have an estimation of least number of edges in case if n in r-1th power is asymptotically less than the number of vertices of a subgraph we will be looking for. However, in all the other cases for the graph, Johnson's graph with R and S, which are not 3 and 1, and when this estimate isn't held, it's an open problem, and it's a field where some research could be done, and we don't know what happened here, and it's some interesting question. So that's all I wanted to discuss. Thank you very much for participating in our problem, in our project, and good luck.
Thank you, Lisa. It was very nice to know about some open problems.